In this video, we're going to talk about work done by a force that varies. Previously, when we talked about work, we kind of made the assumption that the force was a constant. And a lot of times we can use a constant force or an average force, but there's times when you can't. And in particular with springs, we know when we stretch a spring, the farther we stretch it, the more force is required. It takes more and more force to keep going. So if we think about this, let's kind of back up a little bit. If I use a constant force, I can create a graph that looks something like this. Here's the force. Here's my initial position. Here's my final position. So this distance from here to here is your displacement. Here's his force. If I look at this area right here, we can see that this area underneath the curve is simply equal to the force times the displacement. Well, if you think about that, that's actually our definition for the work. The work is equal, of course, we're only talking about the parallel component of the force times the displacement. Like I say, I don't care whether you use an S, whether you use a delta X, whether you use a D, you'll see lots of different things used for displacement. Should probably put a dot for times. We're not doing calculus yet, but if we did, we'd learn in calculus that the area under the force curve on this force position graph gives us displacement. We're going to take that idea, we're going to apply it to a spring or something that obeys Hooke's law. Now, Hooke's law says that the force is equal to K times X. Notice with Hooke's law, as X increases, the force also increases. If we graph that, then, if this is position and this is force, the graph looks like this. The slope is actually K, right? But let's suppose that we want to know the work done to go from 0 to some position X. I know that this height right here, this force, is equal to K times F. If I want to find this area, that's simply a triangle. So what I find is the area under the curve, the work equals the area under the curve. In this case, it's a triangle, so it's 1/2 the base, which is X, times the height, which is KX. And I get that the work is equal to 1/2 KX squared. That is generally the accepted formula for work done by a spring. Now, if the initial position wasn't 0, what if you just wanted to know the work, say, to move from here, call it XI, to here? Well, in this case, we would subtract off this work right here. We just want to go from here to here. So if we don't start at 0, or the equilibrium position of the spring, then our work would equal 1/2 KX final squared, which of course is what we got for the whole thing, minus, and now we just subtract off this small triangle, 1/2 KX I squared. So it's possible that you don't always start with your initial position at X equals 0, so you may want to keep this in mind. If you start with an initial position of 0, you can just say the work is equal to 1/2 KX squared. Let's look at an example and think about this a little bit. Suppose I tell you that a spring is stretched from x equals 0 to x equals 2a. That seems easy enough. The question wants to know is more work done from 0 to a, or from a to 2a. And the work that has more work done stretching the spring for the first half when you move it from 0 to a, or during the second half when you move it from a to 2a, or is it the same? Well, let's think about it. Knowing what we just said, if we want to get the total work, we just want to know how much work is done altogether. If you stretch a spring from x equals 0 from x equal to 2a, so this is basically 0 to 2a, you would use that the work done is 1/2 kx squared, which in this case would be 1/2 k times 2a squared. I'll be sure I get that distance. It's 2a. It's going to be 2ka squared. So whatever the spring constant k is and whatever a is, that's the total amount of work done. What if we just go from 0 to a? If I look at just going from 0 to a, then the work done is 1/2 ka squared. Oh, notice 2ka squared is a lot bigger than 1/2 ka squared. In fact, it's 4 times bigger. If I want to know the work done going from a to 2a, it would just be this total 2ka squared minus the 1/2 ka squared. And you would see that second half was 3/2 ka squared. So notice the work done in the second part is 3 times as large as the work done in the first half. If we look at the picture, that's actually easy to understand. So here's our picture. This is 2a. This is a. If we look at the area under the curve, this triangle and that triangle are identical. In fact, that triangle and that triangle, you can see from 0 to a, that area is basically 1/4 of the total area. And this from a to 2a is 3/4. So 3/4 of that energy, or 3 times as much energy, was used in the second half than in the first half. Why? Because it's harder. As you pull, that force keeps increasing. Let's look at something with some numbers. It's a little more concrete. This one involves a bathroom scale. It says a woman steps on a bathroom scale and she weighs weight 600 newtons, and in doing so she compresses the spring one centimeter. The question wants to know, well, how much work did she do? So presumably before she stood on the bathroom scale, the spring was at its equilibrium position. It was not stretched or compressed. She steps on it, she compresses it 1 centimeter. Well, first of all, we're going to need to figure out what K is, because work is going to be 1/2 kx squared. I don't have K. So if I start with Hooke's law, I know that F equals kx, so the force supplied was 600 newtons. The displacement, she compressed it 1 centimeter, but I have to write that in meters. So if I do 600 newtons divided by 100, I end up getting 60,000 newtons per meter is equal to K. Or if you prefer, 6.0 times 10 to the 4th newtons per meter. So now actually getting work's pretty easy. The work she did in doing that was 1/2 kx squared. So 6 times 10 to the 4th, 0.010 meters squared. This is why it's really important that we change this to meters. You say, well, we could say it was 600 newtons per centimeter, and that's right, 600 newtons per centimeter will work. But if you put that in here, and you put the distance in centimeters, then you don't get units of joules. We want to have consistent units. We want energy in joules. That means we have to measure distances in meters. We have to measure spring constants in newtons per meter. All right, so I put all of this in. Actually, it just comes out to be 3.0 joules, so not that much work. Really big spring constant, but a really small displacement. And notice the displacement is actually a larger factor because it counts twice. Okay, so work done by a spring, 1/2 kx squared. It's an easy formula to use. Let's move on to our next section. When you pick an object up, you do work on it. So let's suppose that you have some object down on the ground and you lift it. Now, in order to lift something, you have to use a force equal to its weight. So we're going to use a force of mg, and we lift it to some height, h. So here's center to center. So the center of mass was here, now the center of mass is here. Or we can go from the bottom to the bottom, but we raise it up some height of h. Use an upward force, upward distance, mgh. Now, when you do work on something, you give it energy. It doesn't have potential energy, it's just, kinetic energy, it's just sitting there. What you did is you gave it potential energy. That's gravitational potential energy. The symbol for gravitational potential energy is a U. U always means potential energy. You also hear say it means internal energy, stored energy. So our potential energy, gravitational potential energy, is just mgh, where h is the distance it lifted. Now, it's really important to understand, only changes in potential energy are important. I'm standing on the second story of my house. I can measure the potential energy of this marker relative to this table, in which case I only raise it about 1/2 meter. Or I could raise it relative to the carpeted floor below me, in which case I've raised it about 1 meter. I could go over here and there's a window you can't see right here, and I could open that window and I could drop it all the way to the ground. I could measure its gravitational potential relative to the ground. So where we say H equals 0 is somewhat arbitrary. It's the changes in potential energy that are significant. However, in this case, if I'm lifting from here to here, the amount of potential energy that I gave it is equal to mgh. And this energy is stored, and it's later going to be able to do work. Let's think about this. Gravity is a conservative force. What that means is that if gravity does work on an object, no mechanical energy is lost. When gravity does work on something, since gravity is conservative, no mechanical energy is lost. So, one way we often think about this, when I take this calculator, it's here in my left hand, and I raise it up, gravity's doing negative work on it. Well, is the object losing kinetic energy? Well, actually, the kinetic energy at the end is the same. I did positive work on it. Gravity did negative work on it. Total work done on it is 0. It didn't gain or lose any speed at the end. There's no change in kinetic energy. Okay? However, what's really important is we didn't lose any mechanical energy. The work that I did, gravity converted to gravitational potential energy. On the way down, if I were to drop this calculator, which I won't because I paid about $100 for it, that gravitational potential energy is not lost. It's simply converted into kinetic energy. So what we see is with conservative forces, if the only forces acting on an object are conservative forces, no mechanical energy is lost. Okay? Now, conservation of energy in general says you cannot lose energy. But a lot of times we have non-conservative forces, like friction, air resistance, and we do lose mechanical energy. We convert the mechanical energy into other forms, in particular heat energy. Okay? So those non-conservative forces like friction and air resistance cause us to lose mechanical energy and gain heat energy. But in this case, if the only force acting on something is conservative, then no mechanical energy is lost. And that gives us basically a statement of conservation of energy that looks like this. When there's no mechanical energy loss, the initial potential plus the initial kinetic have to equal the final potential plus the final kinetic. You can lose potential and gain kinetic, or lose kinetic and gain potential, but the total mechanical energy will be a constant if the only force acting is gravity. Let's look at an example. You throw a baseball straight up. At 20.0 meters per second. How high will it go? Now, you actually already know how to solve this. We're assuming there's no air resistance, using constant acceleration formulas or using kinematics. But this is actually easier to solve using conservation of energy. If you throw a baseball straight up, let's assume, remember, we get to decide where the initial height is 0. So we're going to assume when it leaves my hand, that's an initial height of 0. And I just want to know how high above my hand will it go. The initial potential energy will be 0 because I'm going to say this starting height is h equals 0. It's going to have kinetic energy that's equal to 1/2 mv squared. Whoops, not 15, it's going 20 meters per second squared. And you may go, oh my gosh, Miss Hughes, we don't know the mass. That's true. I actually do know the mass of a baseball, but you know we're not going to need it because look over here. When it reaches the top, I should have drawn a picture. So here's the baseball, goes up 20 meters per second. When it reaches this top, what's the kinetic energy at the very top? Well, at the very top, the speed is equal to 0. If the speed is 0 at the very top, or the velocity is 0, then the kinetic energy is 0. So basically, when you throw it up, it's going to climb until all the kinetic energy that you gave that baseball has been converted into potential energy. So at the very top, the potential energy will be mgh. Oh, and I do know G. I'll have to come back and put G in. But the kinetic energy will be 0. The only thing I don't know is M and H, and M doesn't matter because I have a factor of M on each side. So those actually just cancel out. Doesn't even depend on the mass. So 20 squared is 400, half of 400 is 200, so I get 200 equals 9.80 H. I divide 200 by 9.80, and I find that it will go to a height of 20.4 meters. If my initial kinetic energy is entirely converted to potential energy, it will go this high. Now, if there's air resistance, it won't reach that height. But we're assuming for now we have no non-conservative forces. We have nothing working against us. Now, we could have done it using kinematics. I still know how to do that. We didn't forget. If you want to work it that way, just for fun, let's see. If I was going to use kinematics to work this problem, I would start right here with my picture, and I would say, V equals V0 plus AT. So at the top, the velocity is 0. The initial velocity is 20 minus 9.80 t. And I'd start off by saying, well, how long is it going to go up? And I'd get 20 divided by 9.8. Oh. Get my calculator here. Okay, 20 divided by 9.8. Now, that would be 2.04 seconds going up. So that's the time up. And then I would just say, okay, well, y equals y0, v0 yt plus 1/2 at squared. And I just plug in my numbers. Half of negative, that's going to be minus 4.9. And you know what you're going to get? 20.4 meters. So I had two ways I could work that problem, but it's really simpler to use conservation of energy. To just understand, when you threw it up, it had a certain amount of kinetic energy. On the way up, all of that kinetic energy is getting converted to potential. At the very top, it has 0 kinetic energy. All of the energy is potential. Okay, let's do another example. Let's not do another example. let's talk one more thing and then we'll do another example. What about elastic potential energy? Well, we already said the work done when you stretch or compress a spring is 1/2 kx squared. Well, what happens to that work? If I do work and I compress the spring, an ideal spring will store that work I did as potential energy. So my elastic potential energy, they put an EL, is 1/2 kx squared. Just like gravitational potential energy was the work done in lifting something, gravitational potential energy was mgh. Elastic potential energy is the work you do stretching or compressing a spring. It's 1/2 kx squared. Elastic forces are also conservative forces. So, gravitational forces are conservative, elastic forces are conservative, so conservation of mechanical energy applies. Our potential plus kinetic at the beginning of the problem have to equal our potential plus our kinetic at the end. All right, I'm not sure which number this is in your textbook, but this deals with a glider on an air track. And I wish we had lab experience so you could actually see a glider on an air track. You probably will see a video of some of the homework possibly. So usually an air track kind of looks a little triangular. It's full of all these little holes. And this glider, we have a wall back here, is attached to a spring. So here's my glider. And here's my spring. And if I take this glider and I stretch it over here, not drawn perfectly by any means. So I start off x equals 0, and I'm going to move it 10 centimeters. Well, 10 centimeters is 0.1 meters. And they actually tell me in the problem that I have 3 significant digits, okay? The mass of the glider is 0.200 kilograms. So I have a 200-gram glider. It sits on a frictionless air track. It's connected to a spring with a spring constant. K is equal to 5.00 newtons per meter. It's actually a pretty small spring, really soft, almost like a slinky. It says you pull the mass 0.100 meters and release it with no initial velocity. So, stretched and released, the initial velocity is equal to 0. So you pull it over here, so now the spring looks like this, and you're going to let it go. Okay. Question says, what is its speed at x equals 8 centimeters, or 0.080 meters. Okay, well, let's think about this. Let's think about it in steps. First of all, how much work was done on the glider? equals the work done in stretching it. So the amount of work done really doesn't have anything to do with the mass of the glider. It's just 1/2, 5, and then 0.10 squared. So if I stretch that, let's see what we're going to get. I have 0.5 times 5 times 0.10 squared. I get 0.0250 joules. That's how much work was done. That's also how much potential energy is in the system when I release it, okay? The work you did stretching it, remember that's our elastic potential energy formula. Conservation of energy says this: the initial plus the final, the initial potential plus the initial kinetic equals the final potential plus the final kinetic. All right, in this case at 0.08, it's going to 0.08, it's going to have both potential and kinetic. Right? So let's just plug in our information. We start with an initial kinetic energy of 1/2 kx squared, which we've already calculated. It's going to be this 0.0250 joules, plus a kinetic energy 1/2 mv squared, but v was 0. Initially, the speed's 0. So this is actually just going to be 0. We end up with a final of 1/2 kx squared, and x is 0.08, plus a final kinetic of 1/2 0.2 v final squared. The only thing we don't know in this problem is the final speed. Now, since this is conservative, we can think of this as being the total mechanical energy, that sum. So I've got 0.0250. Okay, so I've already done that. Basically, that's the total energy in the system the whole time. That's how much work you did, that's how much it has. The only question now is how much of its potential, how much of its kinetic. So if I do 1/2 times 5 times 0.08 squared, I get 0.016 joules. So after we let it move, now I don't know what time it is, but at x equals 0.08 meters, you can see that the amount of potential energy has dropped from 0.0250 to 0.0160. That's going to be made up here with this plus 1/2 0.2, which is 0.1 v squared. If I do 0.0250 minus 0.016, I get 0.009 equals 0.1 v squared. Notice all this is saying is that this whole kinetic energy has to equal 0.009. It has to make up the difference. I had 0.025, now my potential is 0.016. It makes sense my kinetic has to be the 0.009. If I finish solving, 0.009 divided by 0.1. Whoops, typed something in funny. 0.009 divided by 0.1. Take a square root. And I get that V equals 0.3 meters per second. You could get plus or minus, but it acts for speed, and I know that the speed is always positive. Whether or not the speed is positive or the velocity is positive or negative depends on which way it's going. If it's going this way, actually the speed will be negative as it passes through point 08. If it's coming back the opposite way, it'd be positive because it actually will vibrate back and forth. Okay. What's interesting here is we can't solve that with kinematics. We don't have constant acceleration here. So I can't use any of my constant acceleration formulas. So it's good that I have conservation of energy to solve a problem like this. Okay, so I'm going to stop here. We're going to do one more video of this chapter.